Hello, welcome to my channel. Over the past month, we have conducted an investigation into the renowned Belousov-Zhabotinsky reaction, or BZ reaction. This is a group of oscillating reactions where transition metal ions catalyze the oxidation of an organic compound, typically mannolic acid, by an acidified bromate solution. Complex patterns can develop over time and space, and the oscillation can repeat itself for dozens or even hundreds of cycles, enabling scientists to study waves and patterns without the need for constant replenishment of the starting materials. For those unfamiliar with this channel, I would like to provide a brief overview of the experiment conducted before. This reaction can be done in either a petri dish or a beaker. Various transition metal ions or complexes such as manganese, cerium, and ferroin, which contains iron, can serve as a catalyst. In this episode, we will examine the original oscillation discovered by Belousov himself, as well as investigate the underlying mechanisms and the mathematical principles governing this process. Prior to this, it is pertinent to provide a historical context for oscillating reactions. These chemical reactions have been recognized for centuries. A notable example is the mercury beating heart reaction. This demonstration illustrates the pulsation of a drop of a mercury metal within an acidic environment in the presence of an oxidizer and an iron nail positioned at a specific distance. Given the toxicity of mercury salts, this demonstration was subsequently replaced by a less hazardous alternative using gallium metal. Despite numerous decades of scientific research, the prevailing belief was that oscillations could only occur in heterogeneous reactions, and the thermodynamic laws prohibit such reactions from happening in an homogeneous, closed system. This has led to the unfortunate event where Belousov's discovery of original oscillation reaction was rejected as an experimental error when he first attempted to publish his findings. Boris Belousov, a Soviet biochemist, was engaged in laboratory research aimed at studying the citric acid cycle. His objective was to synthesize an inorganic analog of this metabolic pathway. When utilizing cerium as a catalyst, he observed that the color of the reaction solution oscillated between colorless and yellow, and the frequency of these oscillations exhibited a linear increase with the temperature elevation. Subsequently, Zhabotinsky replaced citric acid with mannonic acid to establish the most widely utilized version of the Belousov-Zhabotinsky reaction. In this video, we will aim to recreate this historical experiment before investigating the underlying mechanism of the reaction. To start our experiment, we will utilize mannolic acid as the primary ingredient since it has become the most prevalent choice. I have prepared a solution with the same concentration of the ingredients as the previous experiment involving manganese, as discussed in the previous episode. Here is a video clip for a visual representation of my experiment with cerium. After preparing the stock solution, I added approximately 0.5 milliliters of cerium solution. As I sat back, anticipating the visual oscillation between the colorless cerium 3 and the yellow cerium 4, I patiently waited and waited. However, after nearly 10 minutes, nothing seemed to be happening. Concerned that my experiment might be failing, I started to feel a little worried. I was puzzled that this concentration worked for the manganese catalyst and the ferroin catalyst, but not for the cerium. Just before I was about to give up this starting condition and search for a new one, I decided to review my video footage one last time. When I'm playing with normal speed, nothing appeared to be happening. However, when I'm playing it with 10 times of the normal speed, I started to see the whole picture. The reaction was indeed oscillating. I will continue playing this video clip at 10 times of the normal speed to allow the audience to appreciate the oscillation of color. The oscillation period for this particular condition is approximately 35 seconds. Since you are viewing it at 10 times the normal speed, you should observe the oscillation every 3 seconds or so. Here, I added an additional 0.5 milliliter of cerium solution, anticipating a more pronounced color transformation between the two oscillating phases. However, I observed that the extent of color change remained largely unchanged. Here is a side-by-side comparison of the two oscillating phases. As you may observe, the reaction mixture did not achieve complete colorlessness before it reverted back to yellow. The gradual transition from yellow to an even paler yellow over a span of 35 seconds is so subtle that it's almost imperceptible to the naked eye. This really highlights the scientific acumen of Belousov, who meticulously observed and documented this phenomenon before the advent of digital cameras. Now that we have successfully recreated the original BZ reaction using only cerium as a catalyst, we can look at the mechanism of this reaction. According to literature, more than 80 reactions could be happening in this system. For simplicity, 9 key reaction steps were listed here. By understanding them, you would have a deeper understanding of the oscillation nature of this reaction and understand why it would form complex patterns spontaneously. First, let's look at these 9 key reaction steps. Let's first examine reactions 1, 2, 3. In these reactions, the bromate ions, BrO3, are reduced to elemental bromine. The bromide ions are consumed. This is important because when bromide concentration falls below a critical level, reactions 4 and 5 would commence. For simplicity of this video, we can assume bromide is completely consumed at this point. When bromide ions are depleted, the bromous acid, HbRO2, would serve as a reducing agent to reduce the bromate ion to form 2 molecules of bromine dioxide. The bromine dioxide molecule has an unpaired electron and is extremely reactive. It will react with cerium 3 ion in the solution and oxidize it to cerium 4, and it itself will be reduced to bromous acid. So if we add up reaction 4 and 5, you can actually see this illustrates the autocatalytic production of HbRO2 after bromide ions are depleted. So at the beginning of this phase, the concentration of HBrO2 will grow exponentially. The disproportionation of HBrO2 prevents it from growing indefinitely. Nevertheless, the decomposition of HBrO2 wouldn't occur until its concentration reached a certain level. The reason is that the decomposition of HBrO2, as illustrated in equation 6, is a reversible reaction. So it needs to reach a certain level of concentration before this reaction can move forward favorably. Reactions 7 to 9 regenerates bromide ions as well as the cerium 3 ions. As the bromide ions are replenished, the autocatalytic reaction, which was shown in the previous slide, would shut down because bromide ion is a better reducing agent than HBrO2. This completes the entire catalytical cycle for the BZ reaction. You may ask, how does it explain the nature of oscillation? The mechanism behind the oscillation lies in the autocatalytic nature of reactions 5 and 6. When the bromide ions are consumed and this autocatalytic reaction takes over, the concentration of cerium 4 exponentially increases at the beginning of this phase. This leads to a sudden color change in the reaction mixture. Reactions 7 to 9 are relatively slower in nature, but they would gradually catch up. As most of the cerium 3 ions are consumed and the decomposition of HBrO2 started to occur, reactions 7 to 9 would gain momentum. Once the bromide ions reaches the critical concentration, the autocatalytic reaction ceases and the reactions 1 to 3 would resume upon the return of bromide ions. This explains the cyclic nature of this reaction. This graph illustrates the relative concentration between cerium ions and the bromide ions. As you can see, when the bromide ion concentration drops below a critical concentration, the autocatalytic reaction starts to generate a cerium 4 exponentially, causing a sudden color change. However, when bromide ions are replenished by reactions 7 to 9, the autocatalytic reaction was shut down and the cerium 4 ions gradually react with mannolic acid and bromomannolic acid, causing a gradual color change from yellow to a paler yellow. In this graph, you can also see that the cerium 4 ions are never completely consumed and are always present in the reaction mixture, explaining that the reaction mixture never goes to complete colorlessness. At the top of the screen, you are witnessing another run of the original BZ reaction, utilizing only cerium as a catalyst. The video is playing at 15 times the normal speed. When I was conducting the experiments and writing the script of this video, I came to the realization that since the color oscillation of cerium ions is not always readily apparent, we can demonstrate the oscillation nature of the reaction mixture by introducing an additional indicator. If my hypothesis is right, we should be able to observe the color oscillation of another indicator then. Therefore, in a different reaction mixture, I initially added only cerium. This video was captured using time-lapse feature and the color oscillation was challenging to observe. However, after adding a few drops of manganese sulfate solution, the oscillation became more pronounced. That concludes the video for today. Hope you had learned something new today. It takes a lot of time and effort to make a video like this. If you are intrigued by this video, please feel free to like, subscribe, share, and comment so I can make more videos like this. See you next time!